AQA, Combined Science, GCSE, Paper 1, June 19, question 5. And this question is about a kettle. So we've got a heating element, current flows through the heating element, it gets hot, and you're being asked, why does that happen? So it's pretty easy. First thing, just say what's going on. We've got current going through there. So current flows in element. You could just say that there's current in the element. Now this is a bit weird. It's something that you will have done, but maybe not in this context. We explained why a light bulb gets hot, or a filament bulb gets hot when a current flows through it. And it's because the electrons that are moving through this wire collide with the ions in the wire, making them vibrate more, making them hotter. And the same thing's going to happen here. So electrons collide, I can't write, with ions in element. And what's that going to do? That's going to increase their energy. So that's going to increase energy of those particles. Energy of ions or particles in element. So you didn't need to make all of those points, but that's the full story. Basically that one and that one would have done. Right, give this caused problems. One variable that you should have controlled. So one thing that you must keep the same basically for the experiment to make sense. So look at this. So what were they doing? How the mass of water affected the time taken for the water to reach boiling point. So they were changing the mass of water and measuring the time. So the thing that you measure is called the dependent variable. The thing that you change is the independent variable. So what should you keep the same for this to make sense? Now, the exam board will never accept the equipment, because you're not going to change the kettle halfway through. You're finding out about this particular kettle. But if you want to know how long it takes the water to reach boiling point, imagine if you had two kettles. Oh, I'm not even going to draw them. Yes, I am going to draw a kettle. There's kettle 1, and here's kettle 2. And the water that you put in this kettle was at 98 degrees Celsius, and the water that you put in this kettle was 20 degrees Celsius. That one's obviously going to boil before that one. So if you're trying to find out how the amount of water affected it, you'd have confused everything by having different starting temperatures for the water. The start temperature should be the same, which is why that's the answer to this question. The starting temperature of the water has to be the start temperature, not the end temperature, because you're seeing how long it takes to boil, and it will always boil at 100 degrees Celsius. Okay, next part of this question 5, and that's this. Is it this? Yes, it is this. Right, let's have a look at this. So this shows how the mass of the water affected the time taken for the kettle to switch off. Why doesn't it go through the origin? So what are they actually asking when they say that? Because that feels like it's something quite physicsy, but this is actually a common sense question. So if you go home tonight and you turn a kettle on with no water in it, it will not turn off instantly, because something has to get hot for it to register it's hot in order to turn off. So the actual kettle itself has to heat up. So the reason it doesn't go through the origin here, when you have no water in there, it still takes a little while for the kettle to heat up and therefore turn off. So that is that there is time for the kettle to heat up. That's why not. And then it's non-linear. So I mean, why is it not a straight line? You'd think if you double the amount of water, it would take twice as long to heat up. But it doesn't. And the reason for this is that down here, not because of that, but because as the thing gets more full of water, so here's my very badly drawn kettle, as it fills up with water, perhaps the rate at which heat transfers to the surroundings, sort of drawn whiskers, but the rate at which heat transfers to the surroundings is going to change. And therefore this is not going to go up as a straight line. And that's what they were looking for here. So the rate of energy transfer, I've been lazy there, TFER, transfer to surroundings changes. Okie doke. And let's go to the final part of this question, which is a 6-mark calculation. It's designed to be challenging. I'll show you how I would approach it, and maybe you'll be able to access some of these marks. So let's look what they've given us first of all. They've given us that the power is 2,600 watts. It's given us mass, it's given us time, it's given us a temperature change, and hopefully you realise by now, because you've done some work on specific heat capacity, that we want the change in temperature. So theta, the change in temperature, is going to equal 82 degrees. And it wants the specific heat capacity of water. Now, some of you run a mile at this stage, but let's just think, if we need specific heat capacity, what's the equation? So we'll write that down, it's on the equation sheet. E equals mc theta. The questions asked us for the specific heat capacity. The questions told us the temperature change. Here, 82 degrees. It's told us the mass, 0.8 kilograms. But nowhere up there does it tell us energy. So we need to find the energy from somewhere. But hopefully in the back of your mind you should remember that power and energy are linked. Power is the rate of change of energy, or the rate at which energy is transferred. So we do have equations that link those things. We have power equals energy over time. And if you look up here, we've got the P and we've got the T. So we could work out the energy, put it in this equation with the other things that we know, and work out the specific heat capacity. So let's work out the energy. Energy equals power times time equals 312,000 joules. That's 2,600 times 120. Specific heat capacity equation, we get 312,000 equals 0.8 kilograms times C, the thing that we want, times 82 degrees, the temperature change. Should have put a C there, shouldn't I? The only thing we don't know is this C, so if we rearrange it, we get that C equals 312,000 all divided by 0.8 times 82. And that's going to equal a number that rounds to 4,800 joules per kilogram degrees Celsius. Now, I haven't got a calculator with me and I've done this already, but it's important. two significant figures, that means the first two numbers, and the rest need to be zeros, and you need to round it. And that, I think, is the end of that question.